Shayla Bellamy.
And I'm Dylan Harmon.
And this is a picture of our roller coaster that we created. So I want to start with two questions. One, okay, how many of you here have ever ridden on a roller coaster? Okay. How many of you have ever wondered how it worked? Well, we wondered the same thing. So we did some research and we found out that the very initial drop at the start of the roller coaster gives you enough energy to keep you through the entire course. So for us to pose the question, can we create a functioning miniature roller coaster using the principles of roller coaster physics?
Our hypothesis is that if we create a foam roller coaster course with a displacement area of 7 feet, that the marble will have enough gravitational potential energy transferring into kinetic energy to be able to allow it to cruise throughout the entire course.
Our independent variable was the amount of potential energy it had in the displacement area.
For our dependent variable, it was whether or not the marble had enough energy to go through the entire course.
For our experiment, we used 2 needles,
Marbles,
Masking tape,
a yardstick,
a box cutter,
balance scale.
and a stopwatch.
For the velocity is the speed of something in a given direction. And the friction is the resistance that one object encounters when moving across another object.
And for potential energy, it's energy that's stored on the item, as well as kinetic energy, it's energy that's in motion.
and to further demonstrate potential and kinetic energy, I have an example. So this is an inclined plane, and so pretend my hand is a marble. As it's at the top of the ruler, it's 100% potential energy, because the marble has not yet begun to move or convert any potential energy into kinetic. When it moves halfway down, it's 50% kinetic and 50% potential. And at the very end of the roller coaster, it's 100% kinetic, because all of the potential energy has been converted into kinetic energy. For the procedures, we took the pool needles and we cut them lengthwise using the box cutter, and we taped them together into our roller coaster using the masking tape. And our roller coaster was 19 feet long. Then we created 3 checkpoints, one directly before the loop, one directly after, and one near the end of the roller.
For each checkpoint, we calculated the speed, the velocity, the distance, and the timing, as well as the amount of potential energy that's being converted to kinetic.
And this is a video of our roller coaster, which we named like Roly Poly. And we'll play that. And it's kind of hard to see, so we'll play it again. And then this is a picture of our roller coaster, and you can see the checkpoints. Checkpoint 1, which is the red arrow, is right before the loops. Checkpoint 2, blue arrow, is directly after, and checkpoint 3, the green, is near the end of the course.
And so these are our equations for the starting point. I'll zoom in. And then, so for our measurements, we measured 22 degrees from the hypotenuse and adjacent of the starting point to the first checkpoint. And then we measured 2.33 meters on the diagonal path from the starting point to the first checkpoint. And then we measured a 0.59 meter horizontal path from the diagonal path. And for our equation of the velocity, we measure initial velocity squared plus 2 times gravity times distance.
And as well for the acceleration from starting point to checkpoint 1, we use Newton's second law, basically force equals mass times acceleration, and we came with a product of 3.67 meters per second squared.
And to find the velocity at checkpoint 1, we use velocity squared plus 2 times acceleration times distance. And we found that the velocity was 5.35 meters per second.
We calculated how much potential energy is being to kinetic, so we used mass times velocity squared and halving it, and came with a product of 0.072993 joules, as well as in the remaining potential energy, we used mass times gravity times the height, and came with a product of 0.003499 joules. But as energy is being converted, energy is also being lost due to friction. So we used force times distance, and came with a product of 0.01026 newtons.
For the second checkpoint, we found that the potential energy left over was 0.0019 joules. The amount of energy being lost from friction was 0.0051 joules. The kinetic energy still left was 0.069 joules, and and the velocity from checkpoint 2 to checkpoint 3 was 5.213 meters per second.
And for checkpoint 3, we had a conversion of energy of 0.061094 joules. And for our friction, we had an energy loss due to friction of 0.008208 joules, and the friction was for the entire roller coaster.
And you see right here, potential energy from starting point to checkpoint 3 is slowly decreasing, but as for kinetic energy from starting point to checkpoint 1, there's a huge amount of energy gaining, but from checkpoint 2 to checkpoint 3, it's slowly losing. But for the loss of energy, you can see that it loses from checkpoint 1 to checkpoint 2 a huge amount of energy due to the distance and the marble it happens to encounter. So, but as for checkpoint 2, checkpoint 3, it keeps at a constant rate because nothing special is occurring, but the conversion of energy is still in place. Okay.
And this is our chart for our energy versus checkpoint. The first bar is at the starting point, and as you can see, it only has potential energy. This is because the marble has not yet begun to move, so none of the potential energy has been converted into kinetic. For the second bar, it's checkpoint 1, and as you can see, it has a small amount of potential energy left over, and a large amount of kinetic energy, and also a very large amount of loss of energy from friction. This is because from the starting point to checkpoint 1, there was a longer distance than the others, and the speed of the roller coaster resulted in a larger loss of friction. And for checkpoint 2 and checkpoint 3, both of those kinetic and loss of energy goes down. And our last bar is the total energy for the entire roller coaster, including potential and kinetic.
So basically, gravitational potential energy is being converted to kinetic, knowing the velocity and outside factors. Factors such as friction, the sound it produces, the vibration, and the movement of the force. That's velocity, not velocity, but yeah, velocity as it decreases, so to speak. And as gravitational potential energy, as it decreases, kinetic energy is increasing, but also being lost due to friction.
As for our conclusion, the hypotheses have been proven correctly. The marble has had enough energy to allow it to cruise throughout the course. To make this more accurate, we could have secured the roller coaster more to reduce the amount of vibration, which affected our calculation. And then we could have changed the slope of the initial drop to see if that would have changed our data.
One of the other things we could have done was raise the end of the roller coaster to see if it had enough potential and kinetic energy to reach that. And some of the limitations we encountered while doing our experiment was the lack of time and the instability of the